Good evening to all. Today I am going to discuss about a new dual band reflective polarizer based meta surface with higher angular stability for C and expand applications. In previous video I posted work 1 and then introduction to frequency selective surface, and this is related to polarization conversion. So first, when you're moving to the refractive polarizer, first the polarizer, it is nothing but, so first we are going to converting the linear polarization to circular polarization by using the some FSS elements, that is unit cell. So in this related work, so here I consider the elliptical shape FSS. Here we designed the elliptical FSS. So frequency band I chose to here is, that is C band and X band applications I consider. So the frequency band, the center frequency for this elliptical polarizer achieved 7.70 gigahertz, and then another frequency band, that is from X band, that is we achieved center frequency as 9.42 gigahertz. So this is the general frequency, center frequency for both the C and X band for the elliptical FSS, that is elliptical reflective polarizer. So in this work, I converted the linear polarizer to circular polarization. This can be achieved by using the elements of the FSS, that is dimensions which present in the elliptical shape of the FSS elements. And in this work, I achieved the frequency selective surface FSS of less than 3 dB. That is the axial ratio of the corresponding reflective polarizer is less than 3 dB. And then PCR, that is polarization conversion ratio, we achieved maximum as 99.9 percentage for both LHCP and RHCP achieved in the polarizer. So from the surface current distribution, we are confirmed the polarization conversion from LP to CP. This is the main function of the FSS. So once the polarization which achieved the conversion means, so we need to maintain the phase shift of the FSS in the same level. So once the FSS element will achieve the phase shift of 90-degree, then automatically it will converted to the circular polarization conversion polarization. And this work we achieved the maximum angular stability up to 90-degree. So by adjusting the theta value from 0-degree, 30-degree and 60-degree and then 90-degree, the same resonant frequency is maintained for the both the band, that is for C band and as well as the X band. So the main applications of the polarization of the present work is, here we covered C and X band. So maximum it is suitable for the applications such as wireless systems and then radar, and especially in EM shielding and weather radar system, and also in satellite communication application. So these are all the main applications we are using for the FSS polarization in the real-time applications. Next one, this is the proposed FSS design. So first we designed that this is nothing but bottom view, and next one this is the front view. This is back bottom view, and next one front view is designed as, that is proposed FSS. So here we design elliptical FSS. So this is our elliptical FSS. So it consists of two layer, inner layer and an outer layer. So in order to achieve the polarization conversion, we need to maintain a phase shift as 90-degree. So then if once we achieved the phase shift of 90-degree, automatically the LP to CP conversion takes place in the FSS. So this is the general process of the polarization process. So for that, here we design elliptical FSS. So the table represents the dimensions of the FSS. So here I maintain the value, that is inner layer to, here I rotated the angle to inner element to 135-degree. So inner element I rotated to 135-degree and outer element I rotated to 45-degree. So we need to fix the angle in the design of the FSS element. So during the design of the FSS element, we need to fix the rotation angle in the CST tool itself. So then once if we fix the angle, automatically we need to check the results in the surface current distribution and the dual band FSS polarization. That is in simulation, we can identify the conversion process in the results. So after fixing this, so here 135-degree and 145-degree. So if you are taking the phase shift, automatically that is 90 degree. In this proposed FSS, we achieved 90-degree phase shift in the FSS element. So this is the general LP to CP conversion, and dielectric substrate consists of dielectric substrate and conducting sheet, and this is the LP to CP conversion process. And here finally we achieved in the circular polarization, that is CP, reflected polarized wave. And this is the simulation results of the polarization conversion, that is S parameter for both TE and TM mode. So here I covered dual band. So that is 4 to 12 gigahertz, both C and X band I have taken. So in this here up to from 4 to 8 gigahertz, here we achieved one 7.7 center frequency and another point 9.42 gigahertz. That is we covered in C X band. So in this response, here we attain dual band response for both TE and TM mode for the elliptical polarizer. And axial ratio, we achieved axial ratio is less than 3 dB. So by using this formula, we can calculate the axial ratio for the FSS polarizer, that is modulus of Rx square plus Rxy square plus root C divided by modulus of Rx square plus Rxy square minus root C whole power 1 by 2. So C is nothing but this is the value of C. After substituting the values in axial ratio formula, we will get an axial ratio is less than 3 dB for both the band, dual band. Here we attain 7.7 gigahertz, and for here we attain 9.42 gigahertz. So for both the dual band, we attain the axial ratio is less than 3 dB for the elliptical polarizer. And next, this is the polarization conversion response. So from the extracting the, that is after calculating the polarization results, this is the general graph for the PCR. So here we attained 99.9 percentage. So this is the formula for calculating the PCR. So in general, the PCR it measures, that is how effectively the FSS can convert the LP to CP conversion. That is the PCR. So by using this formula, we calculated the PCR value, that is modulus of Rxy the whole square by Rxy whole square plus modulus of Ry by the whole square. So by using this formula, after substituting, we attained the result of 99.9 percentage. The maximum PCR will be attained in the proposed elliptical polarizer of the FSS unit cell. And this is the parametric study of the elliptical FSS. So by adjusting the various elements value, that is width value and the length value, here we attain the different resonant frequency and then different bandwidth of the corresponding elliptical polarizer. So here I varied outer element. OR is nothing but outer element. So I varied outer element from 2.0 mm to 3.5 mm. So here we maintain the same resonance frequency. That is, there is a slight deviations in the response. And after in figure B, here I varied inner radius. That is inner element. That is IR1 from 5.5 mm to 6.5 mm. The different resonant frequency and different dual band will be occurred in the response. And next one, by varying the K1 and K2 value, almost we maintain the same resonant frequency, that is same center frequency in the first band, that is in C band, and there is slight variation in the second band, that is in X band. So by varying the K value from K and K values are equal, K1 and K2 are equal. So by varying the value from 0.35 mm to 0.5 mm, he maintained the same resonant frequency in C band and slightly variation in the second band, that is in X band, 9 to 12 GHz. So this is the parametric result analysis for the elliptical polarizer FSS. And angular stability. So in this work, angular stability, we maintained maximum angular stability as 90 degree. So by adjusting the theta value from 0 to 90 degree, the same center frequency and the same fractional bandwidth is maintained in the elliptical shape FSS. So here in angular stability, I calculated the angular stable for the both TE and TM mode. So for TE mode, I varied from 0, 30, 60 and 90 degree. The same center frequency is attained at both the bands, that is in C band as well as in X band. And similarly for TM mode, I varied from 0 to 90 degree, the same center frequency and then resonant frequency, and as well as the same fractional bandwidth also maintained in the TM mode. And next, by adjusting the theta value from 0 to 90 degree for axial ratio and PCR, we calculated the angular stability of the elliptical FSS polarization converter. So by varying the 0 degree, 30 degree, 60 degree and 90 degree, we maintain the same center frequency, that is in C band 7.42 gigahertz and as well as in 9.42 gigahertz. And similarly, with the PCR, we attained 99.9 percentage. And by adjusting the various different angles from 0 to 90 degree, the same values are maintained in the same frequency, center frequency. And then we maintain the same PCR response for the corresponding angular stability value. So this is the surface current distribution. So by taking the current value, that is surface current distribution, by taking the first band, that is 7.70 gigahertz. Here we attain LHCP, and at 9.4 gigahertz we attain RHCP. So this is the clockwise rotation, and this is the anti-clockwise rotation of the circular conversion process. That is, here we converted LP to CP, and this is the conversion process in the one band. So clockwise direction we attain 1 gigahertz, that is in C band, and RHCP we attain in anti-clockwise, that is in X band. So from the surface current distribution, we confirmed the polarization conversion of the proposed elliptical FSS. And this is the azimuth angle calculation by adjusting the different phi values. So in angular stability, we varied the theta value, and here we varied the azimuth value, that is phi value, that is phase value from 0 degree, 15 degree, 35 degree, and 45 degree. So by adjusting the different phase values, here we confirmed the LP to CP conversion process. So here we attained the LHCP when adjusting the LHCP, that is in clockwise direction at 7.070 gigahertz. We attained the maximum conversion in the 45 degree angle. And next, similarly at RHCP, that is comes to the anti-clockwise direction, that is 0 degree, 15, 35 degree, and 45 degree. The same we attained the conversion process in both the mode. And this is the equivalent circuit for the elliptical polarizer. So for 1 giga, sorry, that is for C band, this is the circuit design, and for higher band, that is when it comes to the X band, this is the circuit design ECM model for the elliptical polarizer. So always the patch element will introduce the inductive element, the gap between the elements will introduce the capacitive elements. So this is the ECM of the elliptical FSS. So here this we simulated in the AWR, and finally we got the same results in compared for as well as in the proposed FSS S11. So this is the dual band frequency response. Here we attained the 7.70 gigahertz and 9.42 gigahertz. So this is the simulation results of the ECM model. So after completing, the prototype will be measured in the anechoic chamber. So this is the simulated and measured results of the elliptical FSS. So there is a slight variations in the measured results. So this slight variation is due to the slight variation is due to the FSS tolerance, that is fabrication tolerance, and as well as the uh, permittivity of the substrate. And this is the measured results of the angular stability for 0 to 90 degree for both the mode TE and TM mode. And for measured values for PCR and as well as the axial ratio, we calculated for both the values, that is from 0 to 90 degree. So always it maintains the axial ratio is less than 3 decibels. And the PCR we calculated, that is maximum percentages 99.9 percentage. So when varied from during the measure the results, we vary theta to 90 degree. The same results will be obtained for both the simulation results and as well as the measured results, the percentage it remains the same as 99.9 percentage. And this is the proposed comparison work with the existing literature work. So here we attain the maximum value as uh, that is the axial ratio we maintain less than 3 dB, and the main advantages of this work is we attain maximum angular stability of 0 to 90 degree. So in existing literature they attain 45 degree, 25 degree and 20 degree and 60 degree, but in proposed work we attain the maximum angular stability of 90 degree, that is from 0 to 90 degree. So this is the advantages of the proposed elliptical FSS polarizer work. And this is the summary of the work. So frequency band I utilized 4 to 12 gigahertz. That is, it covers C and X band. And substrate I utilized Rogers RT 580 with permittivity 2.2 and layer single layer structure, and unit cell maximum size is 14 mm cross 14 mm, and resonant frequency we attain dual band, that is one in the C band, that is 7.70 gigahertz, another band in X band 9.42 gigahertz. So this is the center frequency of the elliptical FSS. And the type of conversion I converted from linear to circular polarization. So that is linear to circular polarization. So the type of polarizer is reflective polarizer, and axial ratio I maintained up to less than 3 dB, and the PCR the maximum range we attained at 99.9 percentage. The angular stability is up to maximum 90 degree we attain in the proposed work when compared to the existing literature work. So application we maximum we covered C and expand, that is mainly we can utilize in the application part like shielding applications, satellite communications for downlink, and then uplink communication process we can utilize for the polarizer work in the corresponding applications, and also we can utilize in the radar communications. Thank you.